The last talk of our session is the third place of the competition, Milad Aghajohari, and I'm sorry for definitely also pronouncing your name wrong.
Yeah, it's Milad Aghajohari. Yeah.
Okay, sorry.
Okay, that's no,
Um,
that's fine.
they were working actually in intercontinental team. I think
Thanks.
the only one that was so diverse, and they used decreed centrality and have a very cool title. Decreed-based features is all you need.
So hello everyone, I'm Milad Aghajohari and I'm presenting for Sanatis Finance 2 team. And thank you for joining our presentation about our submission to the Science4cast competition. I'm sorry if you're tired of presenting dataset, but I kind of want the talk to be complete. So the dataset that we were given was the dynamic graph of the AI literature on arXiv based on the papers that were submitted to arXiv on the AI literature. In this graph, each node is a concept in artificial intelligence research, and we have more than 64,000 of these concepts labeled by the time that the paper was published. So for example, here between concept V1 and V2, we had a paper that connected these two concepts in 1997. Actually, the resolution of the data set was in days, but I'm just showing the year for ease of presentation. And for example, if the paper appears in 1999 that connects V3 and V4 and V4 and V1, at these two edges will be added to the data set, to the graph, and indexed by the time of the publishing of the paper. And the task was to predict the link or whether two concepts will be connected in 2020 by one paper based on the graph until 2017. So for example, we need to predict these two yellow edges by having the blue graph on the evolution of the graph up to that time. So at first I want to analyze a little bit about the data set and why kind of the title of our talk is that the node degree-based features is all you need. As you can see, so it's the history of the node degrees on different years and actually just the last years. And please note that this histogram is plotted in the log scale. As we can see, the number of high degree nodes is increasing linearly in here, which means just it's exponentially growing because it's in log scale. And as you can see, most of the data is concentrated in the last years. In order to study the exponential growth, and I kind of explain the exponential growth of this data set in more detail, we have this plot that shows the number of isolated vertices in this graph, which, as you can see, it's decreasing linearly, but the highest degree in the graph is growing exponentially. And it kind of gives us an intuition about how this graph is formed. So the number of the highest degree is increasing exponentially, which means that the highest degrees are the nodes that are getting connections, getting connected to all other nodes. And I will explain this later in this talk in more detail. And so why the link prediction in this kind of graph is very hard? One of the reasons is that actually we don't have any node or edge attribute. So for example, graph neural net can make use of, because we don't know which concept is which concept in real world. We don't know whether it's document classification, I don't know, deep learning or anything. Also, we don't know anything about the edges. We don't know which paper it was, which title it was, where it was published or anything. And also the number of edges is growing exponentially in this graph. And the most of data is concentrated at the last years, and the distribution of degrees is also changing very vastly. So for example, if you train a model based on the graph on 2016, it will have a hard time generalizing to graph on 2017 because the distribution of attributes, any feature you compute, is kind of changing in time by a high margin. But so we started working on solutions using graph neural networks, and the graph neural networks are developed for dynamic graphs. And we couldn't get anywhere close to like the baseline of the website. We couldn't beat it. And so the moment of epiphany there was when we kind of found this surprisingly powerful baseline. So we were given 1 million pairs of links, and we needed to just sort them. And we just sorted them by the sum of the degree of two nodes or the two concepts in 2017. So we just sorted them by sum of degrees, no machine learning, nothing. And we got a very high accuracy, which showed us that kind of the path that we were chasing with graph neural nets were not very fruitful. And we changed our thinking. And we also found that the kind of degree-based features may be just enough. So we ended up kind of extracting some manual features by kind of theoretical properties of these graphs. We chose some snapshots of this dynamic graph because it's much easier to work with. And it yielded 21 static graphs, and we just chose the last 4 years to work on. And from each one of these graphs, we extract some kind of theoretical properties that are actually very easy. So for example, it's the degree of nodes for U and V. We add the degree of nodes. We add the normalized degree of nodes, which is just the degree divided by the number of edges in the graph. And the reason is, as I said, because the number of edges is growing a lot, we wanted that to be kind of normalized feature. Also, the common neighbors, which is self-explanatory, kind of, it's just the number of neighbors that are in intersection between two nodes. Also, the Jacquard index, we include that in our base features, which is just the number of common neighbors divided by the union of the neighbors. And we can see the distribution of this Jacquard index in different years. And I just want to point out that the distribution is changing a lot. So kind of models will have a hard time generalizing. And also, the average neighbor degree, to differentiate between these two situations, when, for example, one node has 5 neighbors of degree 10 and a node that has one neighbor of degree 500. So the latest features couldn't kind of differentiate between these two. It was here for that. And the other feature was shortest paths. What I wanted to point out, something very interesting that we find out about the shortest path feature, was that in this graph, actually the shortest path, I guess, is not very fruitful because it has very few values. It seems like, so the shortest path is either 3, 4, or 5. And I was surprised when I saw that. And by 3, I mean it has 3 vertices, so its length is 2. I mean, the shortest path between 2 edges that are not connected, right? So it's either 2, 3, or 4. And yeah, so we included it in our features, but I kind of feel, so, I mean, it gives us the intuition that this graph actually has some very huge hubs, and most of the nodes are connected via these hubs. So also we included the page rank, which assigns a score to each vertex of the graph. We didn't find that to be very useful, but well. And also we added the CCPA, which is an interpolation between the number of common neighbors and a centrality feature, which is just the inverse of the shortest path. The one alpha is a hyperparameter. And so these were all our base features, but it doesn't work like these features. If you train a model on them, it's not working very well. So what we did was, in order to encode the temporal kind of value, the temporal property of this graph into our features, we added the difference between the value of the same feature in different years. So for example, here, if P is a feature, and we are calculated for in year A, for node V, and we calculate the difference between this feature P on YB, and we include the difference in our features. And it kind of became our most important feature. So our most important feature based on the post-analysis of our model was just the difference between the sum of degrees of two nodes. So how much the sum of degrees of two nodes is growing in the last year. And based on that, you could get an accuracy of 0.91 or something. So, and the last thing was just feature selection, and we wanted to train some different models based on different features, and then we wanted to post-process them by bagging them. So we chose, we categorized our features to degree-based features, shortest path-based features, which is just the shortest path, and some kind of advanced features like PageRank, Jacquard, or CCPA. And we combined a different number of them with different kind of probabilities. For example, from the degree-based features, because we wanted most of them to be included with 0.75 probability, with less probability the shortest path, and with much less probability the advanced features. We include them in our model, and we train lots of models that we want to bag later. And also we do a random search over the ratio of negative samples we want to train on, because we found out that actually just having 50% negative samples, 50% positive samples doesn't work that will like compare to if you have 66% negative samples and like 33% positive samples. So we want the ratio of negative samples to be more, because we found out that actually the positive samples are rare in the training data or in the test set. So I want to go briefly over what our model is. It's just a gradient boosting classifier. The way it works is that, so for example, in this toyish setup, if you want to predict two edges, to predict the probability of an edge between two nodes based on the sum of degrees at 2015 and sum of degrees at 2016, we want to know whether they have edge in 2017 or not. The way it works is that first we start with a very simple model. We assign a constant budget to the probability. So this model will assign the same probability to all the edges, which is just 0.5. And then this kind of model, the gradient boosting classifier model works like, at first we calculate the residual between what we want the model to predict and what it's predicting. So for example, it's here 1 minus 0.5, it's 0.5. And we train a weak learner, which in this case is a decision tree with depth 1, to guess these residuals and perfect the kind of the prediction of the model. So for example, here, if the sum of degrees at 2015, which is this feature, is bigger than 3,500, the model is going to increase its probability that it's predicting, and if not, it's going to decrease it. And based on this new model, we can calculate the new probabilities and the residuals, and then we can continue to add more and more kind of degrees. And the other thing that we did and actually kind of boosted our performance, and without it, yeah, I think we wouldn't end up third place, was that we found out that so we want our final model, a predictive model, to be invariant to the node order. And so you want the probability that you assign to an edge between U and V to be the same as the probability you assign to V and U, but it's not like obvious how you can do that for a gradient boosting classifier, but it's a very good inductive bias to have. So the thing that we did was just we included the two possible permutations in training data, and we finally tested it on our test set, and in our post-analysis we found that actually the model became invariant, and it boosted our performance by quite a significant amount in the competition. And at the end, when we had trained like 5 models, and we kind of chose the best models that we have and just post-processed the results by averaging the probabilities, we tested using maximum of the probabilities they assigned to an edge, minimum, but the average just worked better. And we just do this post-processing to kind of boost our final submission. And well, so yeah, so it was kind of the end of my presentation. I just want to say that our code is also open sourced on GitHub. And for future directions, so I was saying that we were trying to make it work with graph neural nets, and we couldn't. Maybe if we just merge these features with the GNN, so for example, if we handed it as a edge embedding or node embedding, maybe it will work. I'm not sure, but it can be a very interesting thing to test. We just didn't have time to do that. And also, I wanted to mention that an AUC-based computation can be hacked. And like hacked, I mean, for example, one can extract the ratio of positive samples by a very simple setup. So the only thing you should do is that if you have a positive sample at the first or your first of your ordering, and you just move it to the end and see how much AUC is going to decrease, it gives you a very good estimate of the ratio of positive samples in the test set. And based on our results, we found out that, for example, there are near 7,000 positive samples in this 1 million samples. So, for example, one can infer that, hey, our model should be better on positive samples or anything. I'm just saying that AUC kind of leaks maybe too much of information. And yeah, so it was my presentation. And thank you for your attention. If you have any questions, I would be more than happy to answer them.
Cool. Thank you very much. That was very interesting, especially the last part about hacking the AUC value. I was not aware of that this is possible. What would you actually need to do to make such a practical attack? I think you need to have access to many evaluations, right? So if you would limit the number of evaluation to 5 per team or so, or would this still help?
So I don't know if, for example, 5 per team is practical for a competition. Maybe, I mean, 5 is very low. But the thing is, so if you have infinite access, you can extract the data set by just, if you move something from the first, like the first row to the last row, and see just whether your AUC is increasing or decreasing. Then you find out the true label for that test set. But the thing that I said, for example, the ratio of positive samples with respect to negative samples, it can be just calculated by 2 evaluations. If you have one positive sample that you are sure it's positive, which is not very hard to find, and you at first one submission you put it at your first row, and at the second competition you put it at at your second submission you put it at this final row, the amount of AUC that will decrease would be I don't remember the exact formulation, but it's very easy to compute. So yeah, I mean, based on our computation, it should be near 6,800 positive samples in the 1 million pairs that we were given. So if it's correct, yeah, I think it can be
I see.
done.
I see. Okay, this is really interesting, and there's one follow-up question on exactly this topic. Could this hacking only be done given the current implementation of the AOC, or is this independent of or is this independent property that's for the concept area under the curve?
So sorry, I don't know. Well, I mean, I don't understand. Is the question is that there is another AUC that cannot be hacked? Is it the question?
Yes, but I think you explained that this is a general problem of the area under the curve, right?
Yeah, I think, I don't know if you can use another AUC metric. I mean, well, to be honest, I'm not aware of other ways of calculating AUC. I just think it's kind of an inherent property of AUC that can be hacked in this way. And I actually find a paper that was explaining that AUC, yeah, I think it was a specific paper on AUC-based competitions can be hacked.
Cool.
I see, yeah.
Okay, that's great to know. What would be your suggestion if you make the next competition? What would be the metric that you suggest?
I think, so to be honest, I don't know, because AUC seems to be a very good metric for classification-based competition. Yeah, maybe the answer is just I don't know. Maybe having a kind of a private test set would be helpful. But for example, the thing that I said, kind of leaking the ratio of positive samples, is very hard to avoid. I don't know how one can avoid that. Yeah, so unfortunately, I don't have a very good answer to that. Yeah.
And both Michael and Nock have question about this, or Michael likes it, and Noctran says, I think it will be great for future competitions if you have a hidden test set. It avoids the hacking, and also it avoids the last day spending on minor improvement of the model of the top teams. AOC is a very intuitive and invariant to translation of the probabilities, so that's nice. Yeah. That's a good point in general. I mean, this was a super important comment that you made, which we, if we make similar competitions, should definitely take into account. I had a number of questions actually on your method now. Why did you, or what was the best non-learning result that you got? So where you only played with the degree properties themselves without using the gradient boosting.
Oh, I see. So I think we had just one submission that wasn't using any learning, and that one submission was sorting by degrees. So it was just kind of when one of our team members was frustrated with graph neural networks, like, why can't we beat the baseline that was put on the website, and why can't we just beat that, and why? So he just sorted out by the sum of degrees as a kind of just to see what happens. And then after that, our whole path changed, but we used gradient boosting from the start. So didn't play with that idea of finding something handcrafted by ourselves a lot. So yeah. And well, I mean, the sorting was 0.8997, so it was very close to 0.90.
Okay. Ah, this was the one value you showed. Yeah, it was.
Yeah, it was better than the baseline of the
Yeah.
competition at first. Yeah. So
Yeah, which is again very surprising. Yeah. Then why did you? Yeah, right. You said you used learning and gradient boost, but you used a weak learner. I haven't
yeah.
heard of this before. Could you maybe explain this?
So sorry, I think it's just, I mean, it's kind of the description of the gradient boosting algorithm. I didn't want to say that we have invented a new variant of that. I was just saying that, for example, in gradient boosting, you need to combine the prediction of some, let's say, 100 weak learners. And the reason they are weak is that, so for example, by weak, we mean when you add the prediction of a decision tree of depths 1, or for example, 2 or 3. So they are not very deep. And the reason is just that we don't want it to overfit the data set. So for example, when we let them to have lots of depths, so for example, 20, they just overfit to simple samples and they don't generalize the test set. Yeah, so
I see.
yeah, I mean, it was just explanation of the gradient boosting classifier on the scalearn kind of library. Yeah, it was nothing new by our side on that. Yeah.
Would this be avoidable by using larger data sets? When data set is already large, but
Oh, so is the question that whether I think it will work on
yes, that you can go beyond this weak learner and can go beyond this overfitting that you just mentioned.
So I think gradient boosting, I mean, so I have not played with it that much, but based on the intuition that I have from Kaggle competitions and this kind of things, the gradient boosting classifier is very vulnerable with respect to overfitting. So I have seen it overfit on like very large data sets. So, well, yeah, I think I think it's more about the number of features that are included. So if one decision tree can exactly find as a sample based on its properties, let's say 10 of its properties, then a decision tree with depth 10 is not going to be very fruitful because the learner will just predict the residual based on these 10 features. I mean, you don't want it to kind of memorize, find the sample by some ifs. Yeah, you don't want the number of samples in each leaf to be one. You want it to be bigger because it becomes just a memorization problem in that case. Yeah.
Okay, I understand. There's one more comment by Nima. Very interesting insights, Mila. You have had
Thank you.
You have had a precise look at the data in many aspects. I wonder if you have noticed that the 1 million dataset from 2014 wasn't sampled randomly. This is what I concluded finally. I had 10 times fewer positive example than what random sampler offers. How this could be.
Yeah, so thank you. To be honest, I don't know. Well, I mean, I haven't done the calculation to see what would be the case if we just sample randomly. So yeah, I don't know. Maybe I haven't noticed it yet. Thank you for mentioning that.
Okay. Okay. Cool. Well, thanks a lot for your explanations. Also, thanks a lot for the warning of the hacking. That was very interesting. And congratulations on the third place.
Yeah, thank you. Thank you very much. And thank you for setting up the whole competition.
Sure, was a pleasure. Yeah, if we are here at the end of the competition, I just wanted to say thank you to all of you. It was a really, really awesome day. I learned so much to see how many different approaches, but try to solve this problem that I'm thinking on for a long time. That's really cool to have other people's idea around. Also, thanks a lot for the invited speakers, Rose Yu and Jacob Foster, especially letting us know that we are small scientist ants with limited intellectual capacity. I totally agree somehow. Okay. Well, that was very nice. Yeah, very, very nice talk. So I told you already in the beginning in the email that I would very much like to stay in touch with you. Hopefully writing a cool dataset paper together where we can apply the models and maybe then do some additional interesting things. Um, I will I will reach out then per email again. If you are interested, definitely tell me. Okay, so um,
Yeah, I mean, I was just saying that I would be very eager to kind of work on this project. I think it would be very cool. Thank you.
yes, yes, perfect. Yeah, the more people and the more different ideas, the better, and the more interesting this paper will be, I guess. So, thank you very much. Thanks for your time, and I hope to see you and read you soon again.